Right now, as you sit here watching this, light from a star called Proxima Centauri is racing toward Earth at 300,000 kilometers per second. That light left Proxima Centauri 4 years and 3 months ago. 4 years and 3 months, traveling at the fastest speed anything in this universe can travel, and it is only just now arriving. Proxima Centauri is not some distant, exotic star on the far side of the galaxy. It is the closest star to our Sun. It is our literal next-door neighbor in the cosmos, and it took light, the fastest thing that exists, over 4 years to make the trip. Now, hold that thought, because I want you to consider something. The Milky Way galaxy, our home galaxy, is 100,000 light-years across. That means light, traveling at 300,000 kilometers every single second, takes 100,000 years to cross from one side of our galaxy to the other. 100,000 years. Homo sapiens have only existed for about 300,000 years. Recorded human civilization is only about 5,000 years old. The entire history of everything humans have ever built, every empire, every language, every war, every invention, every poem, every song, could fit 3 times over into the time it takes light to cross just our galaxy. And our galaxy is one of 2 trillion galaxies in the observable universe. 2 trillion, each with hundreds of billions of stars. The observable universe stretches 93 billion light-years from end to end. These are numbers so large that the human brain physically cannot comprehend them. We can say them, we can write them down, but we cannot feel them. We cannot truly grasp what they mean. And yet, these numbers are the starting point of a question that has haunted scientists for over 70 years. A question so simple that a child could ask it, and so profound that the greatest minds in history have failed to answer it. Where is everybody? If the universe is this old, this vast, this filled with stars and planets, then where are the aliens? Where are the signals? Where are the probes? Where are the visitors? Where is the evidence that we are not alone? Because when you look at the numbers, when you really sit down and calculate the probabilities, the universe should be teeming with intelligent life. It should be everywhere. And yet, as far as every telescope, every satellite, every radio dish, every scientific instrument we have ever built can tell us, the universe is silent. Completely, utterly, deafeningly silent. Today, we are going to explore what might be the most unsettling answer to that silence. Not that aliens do not exist. Not that they are hiding. Not that they are ignoring us. But that the universe itself, the laws of physics, the structure of space-time, the brutal realities of distance, energy, radiation, and biology make it fundamentally, permanently, physically impossible for any alien civilization, no matter how advanced, no matter how intelligent, no matter how determined, to ever reach planet Earth. And the same walls that imprison them imprison us. Before we dive in, let me give you some facts that will set the stage for everything that follows. Voyager 1 is the farthest human-made object from Earth. It launched in 1977 and has been flying through space for nearly 5 decades. It travels at roughly 61,000 kilometers per hour, which sounds fast until you realize it has covered only about 1/600th of the distance to Proxima Centauri. At its current speed, Voyager 1 would take over 73,000 years to reach the nearest star. 73,000 years. Human agriculture was invented about 12,000 years ago. The wheel was invented about 5,000 years ago. Voyager 1 would need to travel for more than 6 times the entire history of civilization to reach the star next door. And here is the thing that really makes you pause. The energy required to accelerate even a modest spacecraft to just 10% of the speed of light, which is fast but still means the trip to the nearest star would take over 40 years. That energy exceeds the total annual energy consumption of the United States. Not by a little, by a lot. We are talking about the energy equivalent of millions of nuclear bombs focused into a single act of propulsion. And even if you solved the energy problem, even if you somehow found a way to accelerate your ship, the space between the stars is not empty. Every cubic centimeter of interstellar space contains roughly 1 atom of hydrogen. That sounds like nothing. But at 10% of the speed of light, those atoms hit your spacecraft with the energy of cosmic ray particles. At 50% of light speed, they become lethal. A single grain of interstellar dust smaller than a human cell, would strike your ship with the energy of a small bomb. The void between the stars is not a highway, it is a shooting gallery. And all of this, every single one of these barriers, applies to any civilization anywhere in the universe. The laws of physics are the same everywhere. Einstein's equations do not have exceptions for cleverness. Now, if these facts surprised you, then I want you to know that we have barely scratched the surface. What follows is a journey through the deepest, most fundamental reasons why interstellar travel may be impossible, not just for us, but for every intelligent species that has ever existed or ever will exist. And I want this journey to be one you take with me. So, if this kind of deep scientific exploration excites you, take a moment right now to hit the subscribe button and the notification bell, because this is going to be one of the most thorough, detailed, and mind-bending explorations of this topic you have ever seen. Also, drop a comment right now telling me, do you think aliens have ever visited Earth? I want to see what you think before we go through the evidence. And with that, let us begin. To understand why aliens cannot reach us, you first have to understand where we are, not just our address in the solar system, but our address in the cosmos. And to understand that, you have to grapple with distances that defy human intuition. Let us start small and work our way out. The Moon is about 384,000 kilometers from Earth. Apollo astronauts reached it in about 3 days. That is the farthest any human being has ever traveled from our planet. 3 days to the Moon. Now, Mars. At its closest approach, Mars is about 55 million kilometers away. With current propulsion technology, a trip to Mars takes roughly 7 to 9 months. That is the next realistic destination for human space travel, and it takes the better part of a year to reach. Now, let us go further. The Sun is 150 million kilometers from Earth. We call this distance 1 astronomical unit, or AU. Light covers this distance in about 8 minutes and 20 seconds. When you look at the Sun, you are seeing it as it was 8 minutes ago. If the Sun vanished right now, you would not know for over 8 minutes. Now, here is where things start to get genuinely uncomfortable. The edge of our solar system defined by the Oort cloud, the vast shell of icy objects that surrounds our Sun, extends to roughly 100,000 AU from the Sun. Light takes about 1.6 years to reach the outer edge of the Oort cloud. Our solar system, the entire kingdom of our Sun, takes light over a year and a half to cross. And beyond the Oort cloud, there is nothing. Nothing but the void, the interstellar medium, a near-perfect vacuum stretching in every direction, sprinkled with occasional atoms of hydrogen and tiny grains of dust. And across that void, the nearest star, Proxima Centauri, sits 4.24 light-years away. In kilometers, that is roughly 40 trillion. 40, followed by 12 zeros. To put this in perspective, if you could drive a car at 100 kilometers per hour without stopping, it would take you about 45 million years to reach Proxima Centauri. If you could fly on a commercial airplane at 900 kilometers per hour, it would take about 5 million years. If you traveled on the fastest spacecraft ever launched, the Parker Solar Probe at its peak speed of about 692,000 kilometers per hour, it would take you over 6,000 years. And Proxima Centauri is right next door. The galaxy is 100,000 light-years across. The nearest large galaxy, Andromeda, is 2.5 million light-years away. The observable universe is 93 billion light-years in diameter. Let me give you an analogy that might help. Imagine shrinking the distance from the Earth to the Sun down to 1 inch. Just 1 inch. At that scale, Proxima Centauri would be 4.3 miles away. The center of the Milky Way would be about 1,700 miles away, roughly the distance from New York to Denver. And the edge of the observable universe at this scale would be over 380 million miles from you, which is greater than the actual real distance from the Earth to Jupiter. The universe is not just big. It is so vast that the word big loses all meaning, and it is across these distances that any alien civilization would have to travel to reach us. Distances so enormous that even the most advanced technology we can imagine does not begin to bridge them. Now, you might be thinking, surely in a universe this vast, with trillions of galaxies and sextillions of stars, intelligent life must have evolved elsewhere. And you would be right to think that. The probability seems overwhelming. So let me take you back to the summer of 1950, to a conversation that would become one of the most famous in the history of science. Enrico Fermi was one of the most brilliant physicists who ever lived. He won the Nobel Prize in Physics in 1938. He helped create the first artificial nuclear reactor. He was one of the key scientists of the Manhattan Project, and he had a gift for asking simple questions that cut straight to the heart of the deepest problems. In the summer of 1950, Fermi was visiting Los Alamos National Laboratory in New Mexico. He was walking to lunch with three colleagues, Emil Konopinski, Edward Teller, and Herbert York. They were chatting about recent reports of flying saucers in the newspapers and joking about the possibility of faster-than-light travel. The conversation moved on to other topics. They sat down at their table in the Fuller Lodge, and then, out of nowhere, Fermi looked up and said something that would echo through the decades. The exact words are remembered slightly differently by each person who was there. Teller recalled it as, "Where is everybody?" York remembered it as, "Don't you ever wonder where everybody is?" Konopinski heard it as, "But where is everybody?" Whatever the precise wording, everyone at the table instantly understood what Fermi meant. He was talking about extraterrestrial civilizations. And the question cut like a knife. Here was the logic. The Milky Way contains somewhere between 200 billion and 400 billion stars. Many of those stars are billions of years older than our Sun. A significant fraction of them have planets. Some of those planets sit in the habitable zone where liquid water can exist. If even a tiny, vanishingly small fraction of those planets developed intelligent life, and if even a tiny fraction of those civilizations developed technology, and if even a tiny fraction of those decided to explore or colonize, then given the age of the galaxy, they should have had more than enough time to spread across the entire Milky Way. Even at relatively slow speeds, even at a fraction of 1% of light speed, a civilization could colonize the entire galaxy in 5 to 50 million years. That sounds like a long time until you remember that the galaxy is over 13 billion years old. 50 million years is less than 0.5% of the galaxy's age. So if intelligent life is even moderately common, the galaxy should have been colonized many times over by now. Earth should have been visited. We should see evidence everywhere. And yet we see nothing. This is the Fermi Paradox, and it has haunted astronomers, physicists, and philosophers ever since. Fermi was not actually the first person to notice this problem. In 1686, the French writer Bernard Le Bovier de Fontenelle wrote a dialogue in which one character claims intelligent beings exist on the moon, and another responds, "If that were the case, the moon's inhabitants would already have come to us." The Russian rocket scientist Konstantin Tsiolkovsky raised the same issue in the 1930s, though his philosophical writings were suppressed by the Soviet government. Carl Sagan first mentioned the paradox in print in 1963, and in 1975, the physicist Michael Hart published a detailed examination that categorized possible solutions into 4 types: physical limitations that prevent travel, sociological reasons why aliens choose not to visit, temporal arguments that they have not had enough time, or the possibility that they already visited before humans existed. Hart's paper ignited a firestorm of interest. Frank Tipler responded with a paper arguing that if any advanced civilization existed anywhere in the Milky Way, they would have built self-replicating probes that would have explored the entire galaxy by now. Since we see no such probes, he concluded that we are likely alone. The term Fermi Paradox was coined in 1977 and has been used ever since. And the paradox has real consequences. Senator William Proxmire once cited Tipler's argument when he pushed to terminate NASA's government-funded SETI program in 1981. The silence of the universe has been used as evidence both for and against the search for extraterrestrial intelligence. But what if the answer to Fermi's question is simpler and more brutal than any of the exotic explanations? What if the answer is not that aliens are rare, or hiding, or uninterested, but that the universe itself, through its most fundamental laws, makes it physically impossible for any civilization to cross the distances between the stars? To appreciate why this might be the case, let us first understand why so many scientists expected aliens to be out there in the first place. In 1961, astronomer Frank Drake convened the first scientific meeting dedicated to the search for extraterrestrial intelligence at the Green Bank Observatory in West Virginia. To give the meeting structure, Drake proposed an equation, now known as the Drake equation, that attempted to estimate the number of technologically communicative civilizations in the Milky Way. The equation is n equals r star times fp times ne times fl times fi times fc times l. Let me break down what each of those terms means with the best scientific estimates we have. R star is the rate of star formation in the Milky Way. This is the best known term. Astronomers estimate about 1.5 to 3 new stars form per year in our galaxy. This number is well established through direct observation. Fp is the fraction of those stars that have planets. Thanks to missions like Kepler and TESS, we now know this number is essentially 1. Almost every star has at least one planet. Many have multiple. The Milky Way likely contains more planets than stars. Ne is the number of Earth-like planets per star that have planets. Estimates range from about 0.1 to 0.4. Conservatively, at least 10 to 20% of Sun-like stars have a rocky planet in the habitable zone. That gives us billions of potentially habitable worlds in our galaxy alone. Now we reach the terms that are deeply uncertain. FL is the fraction of habitable planets where life actually develops. Here is where the data becomes troublingly sparse. We have exactly one data point: Earth. Life appeared on Earth remarkably quickly, within the first few 100 million years. This suggests that abiogenesis, the emergence of life from non-living chemistry, might be common, but it also might have been a freak event of almost unimaginable rarity. We simply do not know. Fi is the fraction of life-bearing planets that develop intelligent life. On Earth, life existed for about 3.5 billion years before anything resembling human intelligence evolved. Billions of species have existed, but only one ever built technology. This suggests intelligence is not an inevitable outcome of evolution. Fk is the fraction of intelligent civilizations that develop detectable technology, again, deeply unknown. And L is the lifetime of such civilizations. Do they last 100 years? 1,000? 1,000,000? We have no idea. The first SETI meeting, attended by luminaries including Drake and Carl Sagan, estimated that the Milky Way might contain between 1,000 and 100 million communicative civilizations. Optimistic numbers. But others, like Frank Tipler and John Barrow, plugged in pessimistic values and concluded the number was likely much less than 1 per galaxy. The problem, as researchers Anders Sandberg, Eric Drexler, and Toby Ord showed in a landmark 2018 paper, is that the last 4 terms of the Drake equation are so uncertain that they span hundreds of orders of magnitude. When you properly account for that uncertainty, there is a substantial probability, perhaps 39 to 85%, that we are alone in the entire observable universe. In 2024, scientists published a revised version of the Drake equation that included additional factors like the requirement for plate tectonics and the right ocean-to-land ratio. They estimated that the fraction of planets with the right ocean coverage is between 0.0002 and 0.01. Each additional requirement makes the emergence of technological civilization less and less likely. But here is the crucial point for our discussion. Even if civilizations do exist out there, even if the optimists are right, and there are thousands or millions of them scattered across the Milky Way, the Drake equation tells us nothing about whether they can reach us. It estimates how many might exist and how many might be communicating, but existence and reachability are entirely different things. A civilization could be incredibly advanced, brilliant beyond our imagination, and still be utterly, permanently trapped around its home star. Because the barriers to interstellar travel are not about intelligence or technology. They are about the fundamental structure of reality. And the most fundamental of all those barriers is the speed of light. In 1905, a 26-year-old patent clerk in Bern, Switzerland, published a paper that would rewrite our understanding of space-time and the nature of the universe itself. His name was Albert Einstein, and the paper introduced the special theory of relativity. Among its many revolutionary implications, one stands above all others for our discussion. Nothing in the universe can travel faster than the speed of light in a vacuum. Not almost nothing. Not most things, nothing. This is not a speed limit like a highway sign that you could exceed if you had a faster car. This is a fundamental property of space-time itself. The speed of light is not just a number. It is built into the architecture of reality. It determines how space and time relate to each other. It governs how energy and mass are connected. It is, in a very real sense, the speed at which the universe communicates with itself. Let me explain why nothing can exceed it, because this is so important that it forms the bedrock of everything else in this entire discussion. When an object moves, it possesses kinetic energy. As that object moves faster, it requires more energy to accelerate further. In everyday life, this relationship is approximately linear. Push twice as hard, go roughly twice as fast. But as an object approaches the speed of light, something extraordinary happens. The energy required to accelerate it further does not increase linearly, it increases exponentially. At 90% of the speed of light, the relativistic energy of an object is already about 2.3 times its rest energy. At 99% of light speed, it is about 7.1 times. At 99.9%, it is about 22.4 times. At 99.99%, it is about 70.7 times. And to reach exactly the speed of light, you would need infinite energy. Literally infinite. Not a lot. Not an astronomical amount. Infinite. There is not enough energy in the entire observable universe to accelerate a single grain of sand to the speed of light. This comes from Einstein's mass-energy equivalence. As an object approaches light speed, its effective mass increases without limit. The equation is straightforward. The relativistic factor, called gamma, equals 1 divided by the square root of 1 minus v squared over c squared. As v, the velocity, approaches c, the speed of light, the denominator approaches 0. Gamma approaches infinity. And since energy equals gamma times rest mass times c squared, the energy also approaches infinity. This is not a theory awaiting confirmation. It has been verified in particle accelerators thousands of times. Every day, at facilities like CERN in Geneva, protons are accelerated to 99.999% of the speed of light. Each increase in that string of nines requires exponentially more energy. The Large Hadron Collider, the most powerful particle accelerator ever built, a 27-kilometer ring consuming more electricity than a small city, can push protons to within a hair's breadth of light speed. But it can never reach light speed. The universe will not allow it. Now, some people hear about this speed limit and immediately ask about apparent exceptions. What about quantum entanglement? Does that not allow instantaneous communication? The answer is no. Quantum entanglement is a real phenomenon, experimentally confirmed and recognized with the Nobel Prize in Physics in 2022. When two particles are entangled, measuring the quantum state of one instantaneously determines the state of the other, regardless of distance. But here is the critical point that is often missed. This correlation cannot be used to transmit information. When you measure one entangled particle, you get a random result. The other particle's state is now determined, but the person observing it also sees a random result. They cannot tell from their measurement alone that you have measured your particle. To extract any useful information, you need to compare results to a classical communication channel, which is limited to the speed of light. Multiple experiments and theoretical proofs have confirmed that quantum entanglement cannot be used for faster-than-light communication. The no communication theorem is one of the most well-established results in quantum physics. What about the expansion of the universe? Space itself is expanding faster than light at cosmological distances, as we will discuss later. But this does not help aliens travel faster than light. The expansion of space is not a movement through space. It is the stretching of space itself. You cannot ride the expansion of space to a destination. Objects embedded in space are still bound by the local speed limit. A fish swimming in a river cannot move faster just because the river is flowing. The current carries the fish along, but the fish's speed through the water is still limited by its own swimming ability. Similarly, an alien spacecraft, no matter where it is in the expanding universe, is still bound by the speed of light relative to its local space-time. And so we arrive at a stark reality. The speed of light is approximately 300,000 kilometers per second. That is fast by any earthly standard, but measured against the distances between the stars, it is agonizingly, heartbreakingly slow. Light takes 4.24 years to reach us from Proxima Centauri. It takes about 8.6 years from Sirius, the brightest star in our sky. It takes about 39 years from the TRAPPIST-1 system, which contains 7 Earth-sized planets. It takes about 600 light-years from Kepler-22b, one of the first confirmed planets in a habitable zone. It takes about 1,400 light-years from Kepler 452b, sometimes called Earth's cousin. It takes 25,000 light-years from the center of our own galaxy. And it takes 2.5 million years from Andromeda, the nearest large galaxy. For any alien civilization, these travel times represent minimums that can never be achieved in practice. You cannot travel at the speed of light. You can only approach it at enormous and exponentially increasing energy cost. In reality, a practical interstellar spacecraft, even one using technology far beyond anything we possess, would likely travel at a small fraction of light speed, perhaps 1%, perhaps with extraordinary advances, 10%. At 1% of light speed, the trip to Proxima Centauri takes 424 years. At 10%, it takes 42.4 years. To anywhere further, the numbers become crushing. A trip to the TRAPPIST-1 system, at 10% of light speed, takes 390 years. To the center of the galaxy, 250,000 years. To Andromeda, 25 million years. And these are at 10% of light speed, which, as we're about to see, requires energy that dwarfs anything we can imagine. This brings us to one of the cruelest equations in all of physics, the Tsiolkovsky rocket equation, named after Konstantin Tsiolkovsky, who first derived it in 1897. This equation governs every rocket that has ever flown and every rocket that ever will fly, and it contains within it a truth so harsh that scientists have given it a name, the tyranny of the rocket equation. The equation states that the change in velocity, called delta V, equals the exhaust velocity of the propellant multiplied by the natural logarithm of the ratio of the initial mass to the final mass. In simpler terms, the faster you want to go, the more fuel you need. But the fuel itself has mass, and you need more fuel to carry that fuel. And more fuel to carry that fuel. The relationship is exponential, which means that for high velocities, the amount of fuel required grows absurdly impossibly fast. Let us work through the numbers for interstellar travel. A chemical rocket, like those used in the Apollo missions or the Space Shuttle, has an exhaust velocity of about 4.5 kilometers per second to reach 10% of the speed of light, or about 30,000 kilometers per second, using chemical fuel. You would need a fuel-to-payload mass ratio so enormous that even if the entire observable universe were made of rocket fuel, it would not be enough. I want you to sit with that for a moment. The entire observable universe, 93 billion light-years across, containing 2 trillion galaxies and 200 sextillion stars, converted entirely to rocket fuel, would not contain enough fuel to send a single kilogram to 10% of light speed using chemical propulsion. This is not an engineering problem. This is a mathematical certainty. So, chemical rockets are out. What about nuclear propulsion? Nuclear fission and nuclear fusion offer much higher exhaust velocities. A fusion rocket, for example, might achieve an exhaust velocity of about 10,000 kilometers per second, roughly 2,000 times better than chemical rockets. This is a dramatic improvement, and fusion propulsion is the most realistic advanced propulsion concept scientists have studied. But even with fusion, the numbers are daunting. To accelerate a 1,000-ton spacecraft to 10% of light speed, published physics calculations indicate you would need roughly 1,400 times the spacecraft's mass in fuel. That is 1.4 million tons of fusion fuel for a 1,000-ton ship. And remember, this only gets you to 10% of light speed. The trip to Proxima Centauri still takes over 40 years, and we have not even discussed the return trip, or slowing down when you arrive. Slowing down is its own nightmare. If you want to stop at your destination instead of just flying past it, you need to decelerate. This requires just as much energy as accelerating, which means you need to carry all of your deceleration fuel with you from the start. This effectively squares the fuel ratio. If you needed 1,400 times your ship's mass to accelerate, you now need something on the order of the square of that ratio for a round trip with deceleration. A number so enormous it ceases to have physical meaning. What about the theoretical ultimate fuel, matter-antimatter annihilation? When matter meets antimatter, they annihilate each other completely, converting 100% of their mass into energy via Einstein's famous equation E equals mc squared. This is the most efficient energy release physically possible. Nothing in the universe is more energetically dense. And even with this perfect fuel, reaching 50% of light speed would require a fuel-to-payload ratio of about 10:1. To reach 90% of light speed, over 99% of your total mass must be fuel. And here is the practical problem. As of right now, humanity produces approximately 10 nanograms of antimatter per year, 10 billionths of a gram. The cost, at current production rates, is estimated at about $62.5 trillion per gram. To fuel an interstellar spacecraft, you would need tons of antimatter. At current production rates, manufacturing just 1 gram would take about 100 million years. And storing antimatter is its own unsolved problem, because it annihilates on contact with any normal matter, including the walls of whatever container you try to put it in. Magnetic containment systems exist for tiny quantities, but scaling them up to store tons of antimatter is beyond anything scientists can currently envision. The tyranny of the rocket equation applies to any civilization in the universe that uses reaction-based propulsion, which is to say, any civilization that obeys Newton's third law. For every action, there is an equal and opposite reaction. This law is universal. It does not have loopholes. It does not care how smart you are, whether you are a human engineer or a being of pure crystalline intelligence from a planet orbiting a star in the Andromeda galaxy. If you push mass out the back of your ship to go forward, you are subject to the rocket equation. And the rocket equation says that interstellar travel at any significant fraction of light speed requires either impossible amounts of fuel or a fuel source that does not exist in practical quantities. But the energy problem is only the beginning. Suppose, hypothetically, that an alien civilization somehow solved the fuel problem. Suppose they found a way to accelerate their spacecraft to a significant fraction of the speed of light. They would then face a problem that no amount of engineering can solve: the interstellar medium itself. The space between the stars is often called a vacuum, and compared to the air you are breathing right now, it is astonishingly empty. Earth's atmosphere at sea level contains roughly 10 to the 19th molecules per cubic centimeter. The interstellar medium contains roughly 1 atom per cubic centimeter. That is a difference of 19 orders of magnitude. For all practical purposes, it might as well be nothing. But nothing at rest is very different from nothing at relativistic speeds. At 10% of the speed of light, your spacecraft is moving at 30,000 kilometers per second. At this velocity, even individual hydrogen atoms become projectiles. Each hydrogen atom that strikes the spacecraft deposits energy equivalent to a cosmic ray particle, and you are hitting billions of them every second for every square meter of your spacecraft's forward surface. At 50% of light speed, the energy per atom rises to about 100 million electron volts, or 100 mega electron volts. At 90% of light speed, each hydrogen atom carries giga-electron volt energies, comparable to the particles in a particle accelerator. The cumulative effect is equivalent to a constant, intense beam of radiation bombarding the front of your spacecraft. This radiation would penetrate the hull, damage electronics, degrade structural materials, and deliver lethal radiation doses to any biological occupants. But hydrogen atoms are not the worst of it. The interstellar medium also contains dust grains. These are tiny particles of silicates, carbon compounds, and ices, typically about 0.1 micrometers in diameter, 1/10 of a millionth of a meter, smaller than a bacterium, almost invisible. But at relativistic speeds, these tiny grains carry enormous kinetic energy. A dust grain massing only 100 trillionth of a gram, striking your spacecraft at 50% of light speed, would release energy on the order of several kilograms of TNT. A single microscopic grain hits with the force of a bomb, and there are many such grains scattered through interstellar space. Over a journey of 4 light years, your spacecraft would encounter millions of them. Each one a potential catastrophe. Each one capable of puncturing hull materials, destroying instruments, or triggering chain reactions of secondary damage. Scientists have studied this problem extensively. The conclusions are consistent and sobering. There is no known material that can reliably protect a spacecraft from the combined effects of hydrogen bombardment and dust grain impacts at relativistic speeds. Magnetic shielding has been proposed for charged particles, and it can help with some of the hydrogen problem, but it does nothing against neutral atoms and nothing against dust grains, which carry no charge. Physical shielding, like thick plates of metal or composite materials, adds enormous mass, which circles back to the fuel problem. You need more fuel to carry the shield, which means you need more fuel to carry the fuel for the shield, which means you need more fuel to carry that fuel, and on the tyranny of the rocket equation spirals. Any alien civilization faces the same problem. The interstellar medium is the same everywhere in the galaxy. The physics of high-speed impacts is the same everywhere. A species from a planet orbiting a star 10,000 light-years from Earth would face the same hydrogen atoms, the same dust grains, the same impossible shielding requirements. The universe does not play favorites. And then there is radiation. Not the radiation from the interstellar medium hitting your spacecraft, which we just discussed, but the radiation that permeates all of space. Galactic cosmic rays. These are high-energy particles, mostly protons but also heavier atomic nuclei, that originate from supernovae and other violent cosmic events. They travel at nearly the speed of light and permeate the entire galaxy. Within our solar system, we are partially protected by the sun's magnetic field, which creates a bubble called the heliosphere that deflects some cosmic rays. Earth is further protected by its own magnetic field and thick atmosphere, but once you leave the heliosphere and enter interstellar space, that protection is gone. You are exposed to the full flux of galactic cosmic rays, constantly, for the entire duration of your journey. The biological effects of cosmic radiation are well documented from decades of research aboard the International Space Station, from the Apollo missions, and from extensive animal studies. Cosmic rays damage DNA. They cause double-strand breaks in DNA molecules, which are the most dangerous form of genetic damage because the cell often cannot repair them correctly. This leads to mutations, cell death, and cancer. NASA estimates that astronauts on a Mars mission, which would last roughly 2 to 3 years, would face a 5% increase in lifetime cancer risk. An interstellar journey lasting decades or centuries would expose travelers to cumulative radiation doses far beyond anything a biological organism has ever survived. Beyond cancer, cosmic radiation damages the central nervous system. Animal studies using simulated space radiation have shown cognitive decline, memory impairment, and behavioral changes. It damages the cardiovascular system. Apollo astronauts who spent only a few days beyond Earth's magnetic field showed significantly higher rates of cardiovascular disease later in life. It causes cataracts. It suppresses the immune system. It accelerates aging. Every organ system in the body is vulnerable. Shielding against galactic cosmic rays is extraordinarily difficult. Unlike the charged particles from solar flares, which can be deflected by magnetic fields, the highest energy cosmic rays are so energetic that they blast straight through magnetic shielding. When they hit physical shielding materials, like the hull of a spacecraft, they produce showers of secondary particles, including neutrons and gamma rays, that can be even more biologically damaging than the original cosmic ray. To effectively block the most energetic cosmic rays, you would need meters of water, concrete, or specialized hydrogen-rich materials surrounding the crew habitat. This adds enormous mass, which again feeds back into the fuel problem. There is no lightweight practical solution for cosmic ray shielding that has been demonstrated or even convincingly theorized. For any biological alien species, the same problems apply. Unless alien biology is radically different from anything we can conceive, unless it is somehow immune to ionizing radiation, which contradicts everything we understand about biochemistry and molecular biology, since radiation damages any complex molecular structure regardless of its specific chemistry. Cosmic rays would pose a lethal threat on any interstellar journey of significant duration, and even for artificial intelligence or robotic probes, cosmic rays are a serious problem. High-energy particles cause bit flips in electronic circuits, corrupting data and potentially causing catastrophic system failures. This is a known problem even in Earth orbit, where cosmic ray flux is relatively low. In interstellar space, it would be far more severe. Let me pause here and acknowledge something. We have covered 4 major barriers so far: the speed of light, the fuel problem, the interstellar medium, and cosmic radiation. Each one alone is enough to make interstellar travel extraordinarily difficult. Together, they are devastating. But we are not done, because even if you somehow solved all of these problems, even if you found a way to travel at a significant fraction of light speed, with enough fuel and adequate shielding against both dust and radiation, you would still face a problem that Einstein himself predicted: time dilation. And time dilation does not make interstellar travel easier. It makes it, in many ways, even worse. Time dilation is one of the most experimentally verified predictions of special relativity. As an object moves faster relative to an observer, time passes more slowly for the moving object. This is not an illusion, it is not a matter of perception, it is a real, measurable physical effect. GPS satellites, which orbit Earth at about 14,000 kilometers per hour, experience time dilation. Their atomic clocks tick about 38 microseconds per day faster than clocks on Earth's surface. This is actually a combination of gravitational and velocity-based time dilation, but the velocity component is real and measurable. If GPS systems did not correct for this effect, navigation accuracy would drift by about 10 kilometers per day. Muons, subatomic particles created when cosmic rays strike the upper atmosphere, provide another dramatic confirmation. Muons have a half-life of about 2.2 microseconds. At the speeds they travel, roughly 99.94% of light speed, they should decay long before reaching Earth's surface. But because time passes more slowly for them due to their extreme speed, they live long enough to be detected at ground level. This has been measured and confirmed in countless experiments. Now, let us apply time dilation to interstellar travel. At 90% of the speed of light, the time dilation factor is about 2.3. For every year that passes on the spacecraft, 2.3 years pass back on the home planet. At 99% of light speed, the factor is about 7.1. At 99.9%, it is about 22.4. At 99.99%, it is about 70.7. This might seem like an advantage for the travelers, since their subjective journey is shorter, but it creates devastating problems for any civilization attempting interstellar expansion. Consider an alien civilization that sends a ship to a star 1,000 light-years away, traveling at 99% of the speed of light. From the traveler's perspective, the journey takes about 141 years, still a very long time, still multiple generations, still an enormous engineering and social challenge. But back on the home planet, over 1,010 years have passed. Everyone the travelers knew is dead. The civilization they left may have transformed beyond recognition, collapsed, or been replaced by something entirely different. And the communication problem is even worse. If the travelers reach their destination and send a message back, that message travels at light speed. It takes 1,000 years to arrive. If the home planet sends a reply, another 1,000 years pass. A single exchange of messages takes over 2,000 years. There is no way to maintain a coherent civilization, or even a coherent conversation, across such timescales. Time dilation also means that interstellar colonization, even if the physical barriers could be overcome, would result not in a unified galactic civilization, but in a scattering of completely isolated outposts, each evolving independently for centuries or millennia between any possible contact. There would be no empire, no federation, no communication network, just islands of intelligence drifting ever further apart, separated by gulfs of time as much as space. This is not a science fiction scenario. This is what the physics demands. And it means that, even if aliens could travel between stars, the concept of reaching another civilization is far more complex than simply arriving at a destination. You would arrive in a different time, in a fundamentally changed context, with no ability to meaningfully interact with the civilization you came from. Now, I want to talk about something that goes beyond the physical challenges of the journey itself and addresses a deeper question. Can any civilization survive long enough to develop interstellar travel capability in the first place? This is the concept of the Great Filter, and it is one of the most sobering ideas in all of astrobiology. In 1996, the economist and futurist Robin Hanson published a paper that introduced the concept. Hanson observed that between dead matter and a galaxy-spanning civilization, there are many steps, many hurdles, many transitions, each of which might be extraordinarily unlikely. Somewhere in that chain, Hanson argued, there must be a filter. A step so difficult, so improbable, that almost no lineage of life ever passes through it. The question is, where is the filter? Let us walk through the steps, as Hanson outlined them. Step 1. A habitable star system forms, with a rocky planet in the habitable zone. We now know this step is relatively easy. Kepler and TESS have shown us that such planets are common. Billions of them exist in the Milky Way. Step 2. Self-replicating molecules, something like RNA or DNA, arise from non-living chemistry. This is abiogenesis, and it is the first major candidate for a great filter. Life appeared on Earth within the first few 100 million years, which seems fast, but we have only one example. It could have been a fluke of almost unimaginable rarity. We simply do not know. Step 3. Simple, single-celled life, like prokaryotes, bacteria, and archaea, evolves. On Earth, this happened relatively quickly. Step 4. Complex, single-celled life, eukaryotes, evolves. This is a major candidate for a great filter. On Earth, eukaryotic cells did not appear until roughly 2 billion years after the first prokaryotes. This transition may have required an almost impossibly unlikely endosymbiotic event, where one single-celled organism engulfed another without killing it, and the two became permanently merged. The engulfed organism became the mitochondrion, the powerhouse of the cell, enabling the vastly more complex cellular machinery of eukaryotes. If this event was a billion-to-1 shot, then most planets with simple life may never progress to complex life. Step 5. Sexual reproduction evolves, enabling much faster evolution through genetic recombination. Step 6. Multicellular life evolves. Step 7. Tool-using animals with large brains evolve. This is another strong candidate for a great filter. Despite 3.8 billion years of evolution on Earth and the existence of billions of species over that time, human-level intelligence evolved exactly once. Exactly once. Not twice. Not 10 times. Once. Many species are intelligent in various ways: dolphins, corvids, octopuses, great apes, but none of them independently developed technology or civilization. This strongly suggests that the kind of intelligence that can build spacecraft is not an inevitable outcome of evolution, but a highly contingent, unlikely event. Step 8. That intelligent species develops technological civilization. Even among intelligent species, technology requires very specific prerequisites. You need the right kind of body with manipulative appendages. You need a social structure that enables cooperation and knowledge transfer. You need access to energy sources and raw materials. You need a stable enough environment to allow long-term development. Dolphins may be highly intelligent, but they live in an ocean. They have flippers instead of hands, and they cannot make fire. Intelligence alone is not sufficient. Step 9. That technological civilization survives long enough and advances far enough to achieve interstellar travel capability. This may be the most critical filter of all, because technological civilizations face an array of existential risks that could destroy them long before they reach the stars. Look at human civilization. We have had nuclear weapons since 1945. For over 80 years, we have possessed the ability to destroy ourselves. Climate change threatens global ecological systems. Resource depletion creates economic and social instability. Pandemics, as we saw in 2020, can disrupt global civilization. And now, the development of artificial intelligence introduces entirely new categories of risk that we are only beginning to understand. A civilization that develops the power to destroy itself may, on average, do so before it develops the power to leave its star system. This is a terrifying thought, but it is statistically plausible. If the average technological civilization lasts only a few hundred or a few thousand years before self-destructing, then at any given time, the galaxy might contain very few civilizations, most of which are too young and too technologically limited to attempt interstellar travel. Recent research has added new dimensions to the Great Filter. A February 2026 paper on the ArcSiv preprint server examined the Great Filter hypothesis in detail and identified depopulation as a potential new filter. The authors observed that as civilizations advance and industrialize, birth rates tend to decline. This is well documented on Earth, where virtually every developed nation has a birth rate below replacement level. If this is a universal tendency among advanced civilizations, declining intelligent species may face population collapse before they can achieve interstellar capability. Another paper from January 2026, published on preprints.org, analyzed potential Great Filter events in Earth's evolutionary history, identifying multiple bottleneck points where life on Earth nearly ended. The Great Oxidation Event, the snowball Earth periods, the multiple mass extinctions, any of these could represent filter points that most biospheres fail to survive. The Great Filter, wherever it falls, has a profound implication for our question. If the filter is behind us, if the hard part was evolving complex life or intelligence, then civilizations might be incredibly rare, but those that exist might survive for a long time. But if the filter is ahead of us, if the hard part is surviving long enough to develop interstellar technology, then civilizations might arise frequently, but almost all of them destroy themselves before they ever leave their home system. In either case, the result is the same. The galaxy is not filled with starfaring civilizations. The Great Filter ensures that the number of species actively attempting interstellar travel at any given time is vanishingly small, possibly zero. At this point, I know some of you are thinking about the escape routes, the workarounds, the clever solutions that science fiction has been proposing for decades. Warp drives, wormholes, faster than light travel. Surely, if a civilization is advanced enough, it can find a shortcut around the laws of physics. This is a fair question, and it deserves a thorough, honest answer. So let us examine every proposed shortcut and see what the actual science says. The most famous proposal is the Alcubierre warp drive, named after Mexican physicist Miguel Alcubierre, who proposed it in 1994. Alcubierre showed that Einstein's equations of general relativity technically allow a solution where a bubble of flat space-time moves faster than light by contracting space in front of it and expanding space behind it. Inside the bubble, the spacecraft is not moving through space at all, so it does not violate special relativity's speed limit. The space itself is moving, carrying the ship along. It sounds elegant. It captured the public imagination. It inspired decades of research, and it almost certainly cannot work. The first and most devastating problem is energy. The original Alcubierre metric requires what physicists call exotic matter, a substance with negative energy density. This is not just rare matter, or expensive matter, or hard-to-find matter. It is matter with properties that may not be physically possible. The amount of negative energy required is staggering. Physicists have calculated that creating a warp bubble large enough to contain a human-sized spacecraft would require negative energy equivalent to roughly 10 times all the positive energy in the entire observable universe. Let me say that again. 10 times the energy of every star, every galaxy, every photon, every particle in the observable universe, but negative. And we do not even know if negative energy can exist in the quantities required. The Casimir effect, a quantum phenomenon that produces tiny amounts of negative energy density between closely spaced plates, is sometimes cited as evidence that negative energy exists. But the amounts produced by the Casimir effect are inconceivably small compared to what a warp drive would need. It is like pointing to a single drop of water and claiming it proves you can fill the Pacific Ocean. The second problem is that the Alcubierre warp drive violates all three standard energy conditions of general relativity: the weak energy condition, the strong energy condition, and the dominant energy condition. These are not arbitrary rules. They are physical constraints that describe how energy and matter behave in the real universe. Violating them is not a technicality. It suggests that the solution, while mathematically valid within the equations of general relativity, does not correspond to any physical reality. The third problem is that the interior of the warp bubble is causally disconnected from the bubble wall. This means the pilot inside the bubble cannot control, steer, or stop the warp drive. They cannot send a signal to the bubble wall because the signal cannot travel faster than light within the bubble, and the wall is moving faster than light relative to the outside universe. The pilot is a passenger in a vehicle they cannot control. The fourth problem involves something called the Hawking radiation problem. Calculations show that as the warp bubble travels through space, it accumulates extremely high-energy particles on its front surface. When the bubble decelerates or collapses, this accumulated energy is released in a catastrophic burst that would destroy anything at the destination. You would arrive at your target star system not as a visitor, but as a weapon, annihilating everything in your path. As of 2025, 30 years after Alcubierre's original paper, a scientific consensus, as reported by Space.com, is blunt. We still can't make the math work. Various researchers have proposed modifications that claim to reduce the energy requirements, but these either introduce new physical impossibilities or reduce the energy requirements to merely astronomical rather than infinite. A 2025 analysis published by phys.org examined the question of what physical rules actually prohibit us from building a warp drive and concluded that multiple fundamental physical laws stand in the way. The warp drive is not a technology waiting to be invented. It is a mathematical curiosity that almost certainly does not correspond to any possible physical reality. What about wormholes? Einstein-Rosen bridges, as they are formally known, are theoretical structures predicted by general relativity. They are tunnels through space-time that could connect two distant points, allowing a traveler to bypass the vast distances of normal space. They appear in the mathematics of general relativity, which is what makes them scientifically interesting. But appearing in equations and existing in reality are very different things. The first problem with wormholes is that no observational evidence suggests they exist. No telescope, no detector, no instrument of any kind has ever found any evidence of a wormhole anywhere in the universe. They are purely theoretical constructs. The second problem is that, like warp drives, traversable wormholes require exotic matter with negative energy density to keep them open. Without this exotic matter, the wormhole would collapse in on itself faster than anything could pass through it. The same exotic matter that does not exist in usable quantities for warp drives also does not exist in usable quantities for wormholes. The third problem is stability. Even if a wormhole somehow formed and was somehow held open, it would be extraordinarily unstable. Any perturbation, even a single photon passing through it, might cause it to collapse. And the fourth problem is creation. There is no known mechanism, no physical process, no technology, however advanced, that could create a wormhole. They are not things you build. They would have to be features of space-time that already exist, and we have found none. What about tachyons? Tachyons are hypothetical particles that always travel faster than light. They were first proposed as a theoretical concept in 1967, but they have never been observed. There is no experimental evidence that they exist, and if they did exist, they would create profound paradoxes. Because of the relationship between space and time in special relativity, a particle traveling faster than light in one reference frame would appear to travel backward in time in another reference frame. This would allow the transmission of information into the past, creating causal paradoxes. Most physicists believe that the absence of tachyons is not an accident, but a feature of how the universe is constructed. The universe appears to be specifically designed, if you will, to prevent faster-than-light travel and the causal violations it would entail. What about quantum teleportation? Quantum teleportation is a real phenomenon that has been demonstrated in laboratories. It involves transferring the quantum state of one particle to another particle at a distant location. But it is critically important to understand what is and is not being teleported. Quantum teleportation does not move matter. It does not move energy. It moves information about a quantum state, and it requires a classical communication channel limited to the speed of light to complete the process. You cannot use quantum teleportation to move a person, a spacecraft, or anything physical from one place to another. The name is misleading, a relic of popular science communication. It is not teleportation in any sense that would be useful for interstellar travel. Every proposed shortcut, every clever workaround, every science fiction technology, when examined against the actual physics, either violates known laws of nature, requires materials that do not exist and may be impossible, or simply does not do what people imagine it does. This is not a statement of pessimism. It is a statement of reality. The laws of physics, as best we understand them, do not contain a backdoor for interstellar travel. And these laws are universal. They apply to every civilization in the cosmos, regardless of how advanced, how intelligent, or how technologically sophisticated that civilization might be. Now, let me tell you a story that illustrates this point with painful clarity. In 2016, a Russian billionaire named Yuri Milner stood atop One World Observatory in New York City and announced a project called Breakthrough Starshot. Beside him stood Stephen Hawking, one of the most famous physicists alive, Freeman Dyson, the legendary physicist who proposed that advanced civilizations might build megastructures around stars, Mae Jemison, a former astronaut, a who's who of scientific luminaries. Milner pledged $100 million to develop a technology that could send tiny spacecraft to the nearest star. The concept was elegant. Build a massive array of lasers on Earth with a combined power of 100 gigawatts. Use that laser array to propel tiny light sails, spacecraft weighing about as much as a paperclip, to 20% of the speed of light. At that speed, the probes would reach Alpha Centauri in about 20 years. They would photograph the star system and its planets, and beam the data back to Earth. It was the most serious, most well-funded attempt at interstellar travel in human history. The announcement made headlines around the world. There was a slick video narrated by actor Seth MacFarlane. The media coverage was extensive. A cover story appeared in Scientific American. For a brief moment, it seemed like humanity might actually take its first step toward the stars. The project identified about 30 major technical problems that would need to be solved. 37 research groups were convened. Scientists and engineers began working on the key challenges: the laser array, the light sail material, the nanocraft design, the communication system. Each of these challenges was formidable. The laser system would need to combine millions of smaller lasers into one coherent beam with 100 gigawatts of power. Researchers managed to synchronize tens of lasers in the lab, a genuine breakthrough, but still orders of magnitude short of what was needed. The beam would also need to pass through Earth's atmosphere without being distorted by turbulence, requiring millions of real-time corrections per second. This was identified as potentially the single largest technical hurdle in the entire program. The light sail would need to be 4 meters wide, but weigh only 1 gram. It would need to be highly reflective, absorb minimal laser energy, and withstand acceleration forces of 40,000 times Earth's gravity. The best candidate material, silicon nitride, was fabricated at submicron thicknesses and assembled at millimeter scale, but never at the meter scale required. The communication system would need to send data back from 4.24 light-years away, using instruments small enough to fit on a paperclip mass spacecraft. Scientists explored using the sun as a beacon to aim the transmission toward Earth, using optical instead of radio wavelengths, and building enormous receiver arrays on Earth. But the communication problem was described by multiple scientists involved in the project as the elephant in the room, a challenge that received less attention than it deserved. And then there was the money. Milner had pledged $100 million, but according to scientists who worked on the project, the full amount never materialized. Total spending was estimated at roughly $4.5 million, across about 30 contracts. Philip Lubin, the physicist whose work on laser propulsion inspired the project, received 2 grants totaling less than $200,000, spread over 8 years. His group received less than 5% of their total funding from Breakthrough, with the rest coming from NASA. By 2025, the project was effectively dead. Pete Worden, the executive director, told Scientific American that "We have put the program on hold and are working to transition portions to others." Scientists involved in the project described confusion about its status. Many had heard only informally that it was over. One scientist at the University of Sydney said, "It appears that this project has kind of disappeared. We have not heard from them for probably 2 years." Lubin estimated the project would realistically need 30 to 50 years of intensive work and funding comparable to the Manhattan Project to have any chance of success. The laser power cost would need to drop from $100 per watt to between 1 and 5 cents per watt. The timeline for a possible launch was not 20 years, as Milner had hoped, but at minimum 30 to 40 years, and probably much more. The story of Breakthrough Starshot is not a story of failure, exactly. The science was real, progress was made, knowledge was gained. But it is a story that illuminates the sheer, overwhelming difficulty of interstellar travel, the most well-funded, most prestigious attempt in human history. Backed by billions of dollars of personal wealth, and supported by Nobel laureates and legendary physicists, could not get within a light year of sending a paperclip mass probe to the nearest star. If this is where humanity stands, with all our science, all our technology, all our resources and ambition, then what does this tell us about the feasibility of any civilization bridging the interstellar gulf? The answer is sobering. But perhaps you are thinking about the destination. Perhaps the argument shifts. If the nearest habitable planet is truly Earth-like, truly worth the journey, truly a beacon that would motivate any civilization to attempt the crossing. So let us look at the nearest potentially habitable worlds and ask, are they even worth visiting? The closest known exoplanet in a habitable zone is Proxima Centauri b. It orbits Proxima Centauri 4.24 light-years from Earth. It is roughly Earth-sized and sits within the habitable zone of its star, where liquid water could theoretically exist on the surface. When it was discovered in 2016, there was enormous excitement, an Earth-like planet around the nearest star. But the more scientists have studied Proxima b, the less habitable it appears. Proxima Centauri is a red dwarf star, an M-dwarf, which means it is much smaller, cooler, and dimmer than our Sun. This has several critical consequences. First, the habitable zone is much closer to the star, so Proxima b orbits at only about 7.5 million kilometers, roughly 5% of Earth's distance from the Sun. At this close distance, the planet is almost certainly tidally locked, meaning one side permanently faces the star in eternal day, while the other side is in permanent night. The temperature differential between the two hemispheres would be extreme, with potential consequences for atmospheric circulation and climate stability. Second, and more critically, Proxima Centauri is violently active. Red dwarf stars are prone to intense stellar flares that can be hundreds or thousands of times more powerful than the Sun's largest flares. Proxima Centauri flares frequently and intensely. NASA research has found that Proxima b receives extreme ultraviolet radiation, hundreds of times greater than what Earth receives from the Sun. This radiation would strip away any Earth-like atmosphere over time. Without an atmosphere, there can be no liquid water on the surface, no protection from further radiation, and no possibility for life as we know it. NASA's assessment is stark. An Earth-like atmosphere may not survive Proxima b's orbit. Further out, the TRAPPIST-1 system, 39 light-years from Earth, contains 7 Earth-sized planets, several of which orbit in the habitable zone. But TRAPPIST-1 is also a red dwarf star, with the same flare activity problems. Research suggests that the innermost planets have likely lost their atmospheres entirely, and even the planets in the habitable zone face intense radiation that may make them uninhabitable. The JWST, James Webb Space Telescope, has been studying these planets, and early results suggest that at least some of them lack significant atmospheres. Tau SETI, about 12 light-years away, orbits a Sun-like star and is roughly 4 times Earth's mass, placing it in the super-Earth category. It sits near the inner edge of the habitable zone, which means it might be too hot for liquid water, and the detection itself is uncertain, based on subtle Doppler shifts in the star's light that could have other explanations. The broader picture is this: the nearest stars with potentially habitable planets are either red dwarfs with hostile radiation environments, or are so far away that they compound all the travel problems we have already discussed. Even if a truly Earth-like planet exists within a few dozen light-years of any given alien civilization, the journey to reach it remains physically prohibitive, and the planet itself may turn out to be far less hospitable than distant observations suggest. There is another barrier that we have not yet discussed, and it is perhaps the most existentially disturbing of all. The universe is not static. It is not a fixed stage on which civilizations can slowly, patiently work their way toward each other. The universe is expanding, and it is expanding faster and faster with every passing moment. In 1929, astronomer Edwin Hubble discovered that distant galaxies are moving away from us, and that the farther away a galaxy is, the faster it recedes. This was the first observational evidence that the universe is expanding. Space itself is stretching, carrying galaxies apart like dots on an inflating balloon. Then, in 1998, 2 independent teams of astronomers made one of the most shocking discoveries in the history of science. The expansion of the universe is not slowing down, as everyone expected. It is accelerating. The universe is expanding faster and faster with time. This acceleration is driven by a mysterious force that scientists have named dark energy, which constitutes roughly 68% of the total energy content of the universe. We do not know what dark energy is. We do not understand its mechanism, but its effects are measurable and undeniable. The implications for interstellar travel are profound. The Hubble constant, which measures the current expansion rate of the universe, is approximately 70 kilometers per second per megaparsec. This means that a galaxy 1 megaparsec away, about 3.26 million light-years, is receding from us at 70 kilometers per second. A galaxy 2 megaparsecs away is receding at 140 kilometers per second, and so on. At a distance of about 14 billion light-years, galaxies are receding at the speed of light. Beyond that distance, galaxies are receding faster than light. This does not violate special relativity because it is space itself that is expanding, not objects moving through space, but it means something terrifying for interstellar travelers. The light from galaxies beyond this cosmic horizon will never reach us. Those galaxies are permanently, irreversibly beyond our reach, and we are beyond theirs. No signal, no spacecraft, no information of any kind can ever cross from those regions of the universe to ours. They are, for all practical purposes, in a separate universe, and the cosmic horizon is not fixed. Because the expansion is accelerating, the horizon is effectively shrinking over cosmic time. Galaxies that are currently within our observable universe will eventually cross the horizon and become unreachable. In the far future, trillions of years from now, every galaxy beyond our own local group will have receded beyond the cosmic horizon. Astronomers of the distant future, if any exist, will look out at a sky containing only the merged remnant of the Milky Way and Andromeda, with nothing else visible in any direction. They will have no way to know that the universe was ever any larger. For interstellar travel, this expansion means that the distances between stars and galaxies are constantly, albeit slowly, increasing. A journey planned for 4.24 light-years will actually be slightly longer by the time the ship arrives, because the destination has moved further away during transit. For nearby stars, this effect is tiny, but for more distant targets, across the galaxy or between galaxies, it becomes significant. And it gets worse with time. The longer a civilization waits to attempt interstellar travel, the harder it becomes, because the distances keep growing. The universe is slowly, relentlessly, inexorably pulling everything apart. The islands of the cosmos are drifting away from each other, and the ocean between them is widening. For any alien civilization contemplating a journey to Earth or to any other star, the expanding universe is an additional barrier, one that patience cannot overcome and technology cannot circumvent. Now, at this point in our exploration, there is one argument that remains to be addressed: the argument from advanced technology. The idea that a sufficiently advanced civilization, one that has progressed far beyond our own, could overcome all of these barriers through sheer technological prowess. To evaluate this argument, let us consider the Kardashev scale, the most widely used framework for classifying the technological advancement of civilizations. In 1964, Soviet astronomer Nikolai Kardashev proposed a scale based on a civilization's energy consumption. A Type 1 civilization can harness all the energy available on its planet, roughly 10 to the 16th to 10 to the 17th watts. For comparison, humanity currently uses about 1.8 times 10 to the 13th watts, making us roughly a Type 0.73 civilization. We have not even reached Type 1. A Type 2 civilization can harness all the energy of its star. For a star like our Sun, that is about 3.8 times 10 to the 26th watts. The conceptual technology for this is the Dyson sphere, a hypothetical megastructure that completely surrounds a star and captures its entire energy output. A Type 3 civilization can harness all the energy of its galaxy, roughly 4 times 10 to the 37th watts. The argument goes like this: surely a Type 2 or Type 3 civilization, with access to stellar or galactic levels of energy, could solve the interstellar travel problem. After all, the main barrier is energy, right? Wrong. Energy is one of many barriers, and having more energy does not solve the others. Let me explain. The speed of light does not care how much energy you have. The speed limit is absolute. You can pump infinite energy into a particle and still never quite reach light speed. Having the energy output of an entire star does not change the value of c. It does not change the equations of special relativity. It does not make the universe smaller. A Type 2 civilization with a Dyson sphere has more energy to work with, but the fundamental equations of motion, the rocket equation, the relativistic energy-velocity relationship, all remain exactly the same. Exotic matter with negative energy density does not magically appear when you have lots of positive energy. The Alcubierre warp drive requires negative energy, not just enormous amounts of positive energy. Having a Dyson sphere does not help you create exotic matter. It does not exist in any form we can produce, regardless of energy availability. The interstellar medium is still there. The hydrogen atoms, the dust grains. A Type 2 civilization spacecraft still has to fly through it. The physics of high-speed impacts do not change, because the civilization that built the ship is more advanced. Shielding is still necessary, still massive, and still feeds back into the fuel problem. Cosmic radiation is still lethal. A Type 2 civilization's biological organisms, if they have any, are still made of molecules that can be damaged by ionizing radiation. Their electronics still suffer from bit flips and degradation. Time dilation still applies. A Type 2 civilization's clocks still slow down when their ships travel at relativistic speeds. Their travelers still arrive in a changed future. Their communications still take years, decades, or centuries to cross interstellar distances. This is a crucial point that is often overlooked in discussions of alien technology. Advancing on the Kardashev scale gives you more energy, but it does not change the laws of physics. It does not rewrite the equations of general and special relativity. It does not eliminate the interstellar medium. It does not stop the expansion of the universe. It does not cure the effects of radiation on complex molecular structures. Technology operates within the framework of physics. No amount of technological advancement can exceed the framework itself. You can build a faster car, but you cannot repeal the law of gravity. And here is something else worth noting. Despite decades of searching, we have found no evidence of any Type 2 or Type 3 civilization anywhere in the observable universe. Extensive surveys have searched for Dyson spheres, which would be detectable as stars with unusual infrared signatures. Some candidate stars have been identified, most famously Tabby's star, KIC 846, 2852, which showed unusual dimming patterns that briefly suggested an artificial megastructure. But subsequent research found natural explanations, most likely dust clouds orbiting the star. Breakthrough Listen, the most comprehensive SETI program ever conducted, has surveyed millions of stars and found no confirmed artificial signals. The Hart-Tipler conjecture takes this a step further. If self-replicating probes, often called von Neumann probes after mathematician John von Neumann, are possible, then even a single civilization in the Milky Way should have been able to explore the entire galaxy within a few million years by sending out probes that replicate themselves at each new star system. The probes would spread exponentially, reaching every star in the galaxy in cosmologically brief period. Yet we see no evidence of such probes, no artifacts in our solar system, no unusual signals from neighboring stars, nothing. This either means no civilization has ever built von Neumann probes, which suggests the barriers to interstellar technology are insurmountable, or it means such probes are fundamentally harder to build than the theoretical models suggest. Let us now confront yet another aspect of this isolation, the difficulty of even communicating across interstellar distances, let alone traveling them. Because if aliens cannot reach us physically, perhaps they could at least send us a message. Perhaps they have been shouting into the void, and we simply have not heard them yet. The reality is that even interstellar communication faces daunting, perhaps insurmountable challenges. Humans have been listening for alien signals since 1960, when astronomer Frank Drake conducted Project Ozma, pointing a radio telescope at two nearby sun-like stars and listening for artificial signals. Since then, dozens of SETI projects have searched the skies. The most ambitious, Breakthrough Listen, funded with $100 million by the same Yuri Milner who backed Starshot, has surveyed millions of stars using some of the most sensitive radio and optical telescopes on Earth. The result, after more than 60 years of searching, is silence. But the silence might not be surprising when you understand the physics of interstellar signal detection. Radio signals, like all electromagnetic radiation, obey the inverse square law. This means that when you double the distance from a signal source, the signal strength drops to 1/4. Triple the distance, and it drops to 1/9. By the time a signal has traveled several light years, it has been diluted across an enormous sphere of space. Earth's television and radio broadcasts, which some people imagine as a beacon detectable by alien civilizations, become indistinguishable from background noise within a few light years. As of the most recent assessments, Earth's most sensitive radio telescopes could not detect non-directional radio signals, like those leaked from a civilization's everyday technology, even at a fraction of a light year. Detecting alien signals would require either enormously powerful, deliberate beacons focused directly at us, or receivers far more sensitive than anything we currently possess. And even then, the searcher faces the directionality problem. Space is three-dimensional. A signal beam aimed at a specific star must be pointed with extraordinary precision, and the receiver must be pointed back at the source with equal precision. But you do not know where the signal is coming from, and the sender does not know exactly where you are. You are both shooting in the dark, hoping to accidentally cross beams. The electromagnetic spectrum is also vast. What frequency should you listen on? The hydrogen line at 1420 MHz, suggested by some as a universal frequency? The water hole, the range between hydrogen and hydroxyl lines? Optical frequencies? Infrared. There is no agreed upon universal channel, and searching all possible frequencies at all possible times in all possible directions is a task that dwarfs anything human technology can currently accomplish. And then there is the time problem. Radio signals travel at the speed of light. A message from a civilization 1,000 light years away takes 1,000 years to arrive. By the time we receive it, the civilization that sent it might have collapsed, evolved into something unrecognizable, or simply stopped transmitting. And if we send a reply, it takes another 1,000 years to reach them. A single exchange of messages, a simple hello and hello back, takes 2,000 years. No meaningful conversation is possible. No exchange of technology, no cultural exchange, no diplomacy. Just isolated signals crossing in the void, separated by gulfs of time that make the distance between sender and receiver almost irrelevant. There is also the encoding problem, which is rarely discussed but critically important. If we did receive an alien signal, how would we decode it? We share no language with any alien civilization. We share no cultural references. We may not even share the same sensory modalities. An alien that communicates primarily through chemical signals or gravitational waves might encode its messages in ways that are completely opaque to us. The assumption that a sufficiently intelligent species would send mathematically based messages starting with prime numbers or the digits of pi is reasonable but unproven, and even mathematical messages would require enormous effort to decode beyond the most basic level. The SETI scientist Jill Tarter once compared the search for alien signals to searching for a fish in the ocean. The electromagnetic spectrum is the ocean, and we have examined in 60+ years the equivalent of a single glass of water. We may simply not have looked long enough in the right place, at the right frequency. But this argument, while fair, also underscores the difficulty of the enterprise. If 60 years of searching with increasingly powerful instruments has yielded nothing, the universe is either empty of communicating civilizations, or the barriers to interstellar communication are far more formidable than we imagined. If you have followed me this far, you now have a comprehensive picture of the barriers that prevent interstellar travel. Let me bring them all together, because the cumulative weight of these barriers is greater than any one of them alone. Barrier 1. Cosmic distances. The nearest star is 4.24 light-years away. The galaxy is 100,000 light-years across. The observable universe is 93 billion light-years in diameter. These distances are so vast that they defy intuition, and they impose minimum travel times that stretch across centuries, millennia, or millions of years.